Hey there, everybody, and welcome to Napkin Physics. Just a brief overview of what Napkin Physics is. I am a flight medic, and commonly I do not see enough physics, chemistry, biochemistry within the community of medicine, and specifically pre-hospital medicine. So what I'm going to attempt to do is, within 5 minutes, get some physics equations, maybe some metabolic reasoning and processes to the EMS community so they can better understand what's happening to their patient, how they can treat their patient, how they can use their equipments, all through physics. So we got 5 minutes on the clock. Let's rock and roll. A little bit of business first. It is sponsored by EM Transport Radio, the podcast, and Squad 81, but we will get to that at the end. We got time clicking here. All right. Today we are going over Posisuille's equation, and I know a lot of you are like, oh God, no, not an equation. Math, I hate math. Me and math don't mix. Well, that is bullshit. Everybody can do math. The main thing you got to know is there ain't no magic in the breakdown, baby, as the great sage Francis has taught us. So let's break down this equation and understand what we are actually looking for. What are we solving for? We are solving for F. We are solving for flow. And when we talk about flow today, you could actually use this F or this Q that it's commonly used in for a couple different things. But we are going to look at it for fluid flow through a tube, through a catheter, through a cylindrical device. And it'll be really relevant, and you'll be able to understand a lot better when we break each of these down. So delta P, when we talk about change in pressure, that's all that means, times pi, times the radius of a catheter to the fourth power. This is all going to be divided by 8 over the viscosity of a fluid, that's what this N is, and then L, which is length of a catheter. Now, don't worry, I'm not going to leave you guys in the lurch. We are going to break down each of these one by one. So delta P, change in pressure. Well, what is a change in pressure, Charlie? Well, I can show you. Let's talk about a tube. How about we talk about an artery? Let's talk about our aorta. This is going to be a great one. So we have pressure on this side, and we have pressure on this side. So this initial pressure over here is just that, an initial pressure. Over here is a final pressure. And when we can think about it is, let's say we got our heart over here, right? If we increase contractility, we are going to increase pressure on this side. We are also going to increase pressure on this side when that fluid flows through that vasculature. So how does that equate to delta P? Well, that equates just like this. It's going to be pressure final minus pressure initial. And that is how you equate delta P. Now, let's check out pi. Pi, well, is just that, pi, or 3.14, which is a constant that's going to be remained constant throughout the entirety of the use of this equation. We really can't change pi. It's an already set in number. Now, this is a big one. Radius of a catheter. Everybody remember this. Radius of a catheter. And here's why. It's to the power of 4. Now that is a huge difference. And you guys probably know this difference already. So if we have a 20 gauge catheter, and now we insert on the other side a 14 gauge catheter, we already know that this 14 gauge catheter is going to push in fluid so much quicker. But why? Why does it do that? Let's go back to that catheter. Now, when we see fluid go through a catheter, what it actually does is hit the side of the catheter. There's fluid getting not attached to, because it's actually made out of a special polymer that it's made of, but it goes through this fluid, but it has turbulent flow when it hits the sides of these catheter. And then it has laminar flow through the middle of this catheter. So as you can see, if we look at this, there will be turbulent flow throughout a lot of this catheter. And if we look at this catheter, and if we take the same size, it will actually have a lot more laminar flow that comes out the center of this catheter just because it has that greater lumen. Now, let's keep moving on. 8, well, that's relatively simple. That's going to equal 7 plus 1 or 9 minus 1. You already know what 8 is. Next one is flow or viscosity of a fluid. And this is important because there are actually a couple different viscosities of fluid that you can give, right? We all have D10, we have D5W in the field, we have D50, we have all this stuff. And you know what? This is actually pretty important in the fluid that you're administering. Is normal saline going to be more or less viscous than whole blood when we get that blood in there? I think it's going to be actually less viscous than whole blood. Now, here's something that's important. In Impella devices, the viscosity of the fluid does make a change in the way it works. So N stands for viscosity of the fluid through the tube that you are administering. Now, the last one, L. Now, this is relatively easy, length of a tube. Now, we actually... this is a relatively easy thought process. When we think of length of a tube, which one of these is going to have more turbulent flow inside the tube itself? Well, this one is. It has more surface area for that turbulent flow to act on. Look at all that surface area. This one is much shorter. So if we want really rapid fluid administration, we get that short, fat tube. Now, let's do a little bit of a thought experiment. So we have Poussey's equation back up. Now you guys know all these things. You guys understand what each one stands for. Now let's break it down. Delta P. If we increase the pressure within inside our vasculature, let's say let's do this. We put a pressure bag on our catheter, on our 10 drop set, whatever. We increase the pressure. What's that going to do to the flow? That's right, that's going to increase the flow. Well, now let's move on to pi. Well, pi is a constant. We can knock both of these out. Well, now let's go to, let's say, length. If we increase our length of our catheter, increase the length of a catheter, what's that going to do to the flow? That's right, it's going to decrease the flow. Now, let's say we are pushing in, some D5W, and now they say, hey, you know what, let's push in some D10. What is it going to do to the flow if we increase the viscosity of the fluid we're doing? Well, that's going to decrease this flow. Now the last one, this is the big one. This is the reason it's so important. Now, if we increase this radius, say we have a catheter at a 18 gauge, and we say we want a 16 gauge catheter. That's a little bit larger. What is that going to do to the flow? Well, since it is to the power of 4, that flow is going to be monumentally increased by the radius of that catheter. Now, in the next video, we will actually go over a couple medical solutions and medical quandaries that have to do with this equation. So I hope you guys enjoyed this brief overview of the Poussey's equation, a brief introduction. We did go over our time, but I'll try to keep it down in the next few videos. And this is just a little bit of stuff where you can reach me, and we can talk, and all the social media. So emtransportradio@yahoo.com. Our website is going to be radio.squarespace.com, and this is Twitter, and you can find us at emtransport81. This is Google Plus. You can just type in my name, Charlie Alvarenga, and this is Instagram, and you can reach me at Papa Bear Medic. Now, you guys all have a great day, and remember that every patient is family. See you in the next one.